Hey everyone, welcome back to my YouTube channel. Please subscribe if you're new here. In this video, we'll take a look at an interesting problem called the reverse Polish notation calculator using Haskell. And we will also see how to think functionally to solve this problem as elegantly as possible. So, usually when we write a mathematical expression, in school we write them in an infix manner. For instance, we write it as 10 minus 4 plus 3 into 2. Here, the into, plus, and minus are infix operators, just like we have infix operators in Haskell, like the plus, the lm, and so on and so forth. Okay? This makes it handy because we as humans can parse it easily in our minds by looking at such an expression. But there is a downside to it. Can you think what it is? Yes, we have to use parentheses to denote the precedence. So a reverse Polish notation is another way of writing down mathematical expressions. Initially, I do agree it looks a bit weird, but it's actually pretty easy to understand and use because there's no need for parentheses. Yes, you heard me right. There's no need for parentheses in reverse Polish notation. And it's very easy to punch into a calculator. While most modern calculators use infix notation, some people still swear by RPN calculators. This is what the previous infix expression, which was infix, was 10 minus 4 plus 3 into 2. Excuse my bad handwriting. In reverse Polish notation, I'll write it as RPN for short, will look like 10, 4, 3 plus 2 into minus. Okay, so how do we calculate the result of whatever this is? So well, let's think of a stack, shall we? So let me just move it the whiteboard down here so that I have sufficient space. Let's write 10, 4, 3 plus 2 into minus. So what we do is we traverse from left to right and we maintain a stack. So a little bit of stack prerequisite is required here. And whenever we see a number like this one, we just push it inside the stack 10. And when we reach 4, we again push it 10, 4. So stack, as you know, follows LIFO principle, last in, first out. And 3 again is a number. So 10, 4, 3. And now here it's an exception because this plus is not a number, it is an operator. So what to do now? So what we do here is that whenever we approach or uh, arrive at an operator, we pop out the top two elements and we perform the operation with the operator. So 3 and 4 are popped out and we perform 3 plus 4 and the result, which is 7, will be pushed back in. Pushed back in. Again, please excuse my bad handwriting. So over here, it will be 10, 3 and 4 are popped, and we perform this addition and we push it back in. Okay. Uh, Let me just write it space. Okay. Now again, we approach a number, so we push it back inside. And now here we again arrive at an operator. So we pop the first 2 and 7, and we perform the multiplication 14, and the 14 is pushed back in. And here we reach the minus. So note the thing here is that the first element which is popped out, the first element which is popped out is actually the operand 2, not operand 1. And the second element is the operator 1. What does it mean? So when you pop out 14 and 10, you are supposed to perform 10 minus 14, not 14 minus 10. Now, why didn't I mention it earlier? Because it was plus and multiplication, and the order does not matter. But in division and minus, the order does matter. So the first element popped is the second, the OP2. So, and we perform 14 minus 10 minus 14, sorry, 10 minus 14, and the result, which is minus 4, is pushed back in. And this final number is our answer to this wonderful RPN expression, minus 4. Got it? So uh, let me just clear everything. Okay, this looks a lot cleaner. Okay, now that we know how we calculate any RPN expression by hand, let's think about how we could make a Haskell function that takes this parameter as a string. What is the parameter? Our very own example, 10, 4, 3 plus 2 into minus as a string input, and should return minus 4 as our output. The output, this is our input, right? So how do we achieve that? So a pro tip from my side is that it really helps to think first what the type declaration of the function which we are going to create should be before concerning ourselves with the implementation and then writing it down. In Haskell, a type declaration tells us a whole lot about the function due to the very strong type system the system has. So what would be our uh, type declaration? Here I am in Visual Studio Code. You can use any text editor of your choice. So let's create a custom function solve RPN, which is going to take, as I said, a string of reverse polish notation and gives us the back computed result. So let's declare now A as type class num, and it accepts a string, and it should return an A, right? So cool. We have the type declaration, which in itself makes it a lot cleaner on what we are trying to do. We are trying to accept a string and return A, which is of type class num. Great. And when implementing a solution in Haskell, it's also good to think back on how you did it by hand or dry run, and maybe try to see if you can gain any insight from that. So try to remember how we solved it using a stack manually. So I'll give you a hint. So it might help if we start by breaking this string 10 plus 10, 4, 3 plus 2 multiplication minus as 10, comma 4, comma 3, comma plus, comma, again excuse my handwriting, comma minus. So this string And note here I'm separating each number and operator with space, and I'm trying to convert it into a list where each element is differentiated, each element is separated. So what did we do the list of items in our head? We went over it from left to right and kept a stack as we did that, right? So does the what I said remind you of anything? Remember an important helper which comes to us, which is folds. Yes, folds. Right. So there are two types of folds in Haskell, as you may know, fold R and fold L, fold right fold and left fold. And these come to our rescue in this case. So in this case, we are going to use the left fold. Why? Because we traversed expression from left to right. Simple. And the accumulator value will be our stack. And hence, the result from the fold will also be a stack. So we must decide how to represent the stack, right? So my suggestion is that we use a list. A list. Also, I propose that we keep the top of our stack as the head of the list. That's because adding to the head of a list is much faster than adding to the end of it. So if we have a stack, say 10, 4, 3, we'll represent it as a list 10, 3, sorry, 3, 4, 10, right? Now we have enough information to roughly sketch our function. It's going to, our function is going to take a string like, let's say 10, 4, 3 plus 2 into minus as input and break them down into a list of items using words function. Yes, remember the words function? Use words and it will return. Let me just comment this line out. It will return what? It will return 10, 4, minus, right? So this is how the return of the words function will be. So next we'll do a left fold over the list and end up with a stack that has a single item. So a stack which has a single item which will be minus 4, right, as we see in our dry run. So as we're using a lot of list function, it is very helpful to import the list function in list module. So import data.list to help, which reduces our pain of creating custom functions. We can just use the predefined function. To solve RPN, let's take the expression. So this expression is our string of 10, 4, 3, that one. And what are we going to do? We are going to use words expression to get this, right? And what are we going to do with this? Well, we are going to apply a folding function. Great. What fold? Fold left fold, because we are traversing from left to right. Yes, that's it. And using a fold function, as you know, will accept a function. Let's call it folding function for now, and an accumulator. Accumulator will be our stack, and now we represent it using an empty list. Great. So what will be our final result? Well, it will be the head of our stack. Actually, it's going to be anyway a single element, but we should return an element of type num. And if we don't use head, it's going to return a list of single element, whereas head is going to just take the single element and return it to us, in this case a number. And now an ambiguity exists here. What is this folding function? Well, Haskell doesn't know. So we are going to tell what this folding function is. Folding function, and it's going to accept a stack and an item and do something with it. Great, great, great. So let's think about a condition when a number exists. When a number exists, we should simply add it to our stack, isn't it? So folding function, if it is a stack and stack and a number string, what we do, we just add the number, right? So read number string, which will convert the string in integer, and prepend it to access, which is a stack, just which will act like a pushing the number into the stack, right? And now folding function. And now what if a plus operator comes? So let's split our stack like this. And what if plus appears? So what we'll do, we just take x and y, we just simply add it and prepend it to our y's. And similarly, what will happen if multiplication comes? Simple, the same thing. X into y colon ys. And what if subtraction comes? Now here's a point to remember. I told you the first operator, we should add y minus x ys, not x minus y ys, because the first element popped out will be the second operator operand. Okay, great. So as we are using read, let's add the read type class to it as well. Let's run this program using ghci colon L and the name of the file to import. And say solve rpn. Let's give our very own example 10. What was it? 10 4 3 plus 2 asterisk minus. Oops. Solve rpn 10 4 3 plus 2 minus 4. Here you go. You can try out various examples like this. So that's it, guys. I hope you have had a wonderful time doing this. Thank you and subscribe for more such videos.